All right, welcome everyone. Thank you very much for tuning in. My name is Ryan Hodgson. I'm a third year undergraduate student at the German Meteorological Services Training Center. I'm part of a team of 4 students, and together we would like to give you a presentation on the cut-off low that hit Spain in October this year. My fellow teammates are Melissa Wirtz, Saskia May, and Ola Müller-Susemir. If you've got any questions or problems that come up during the talk, please feel free to use the chat feature and text us. Without further ado, let me begin by giving you a short overview of the structure of our presentation. We've split our presentation into 4 parts. First, we would like to start with definitions of the relevant terms that we're going to use. And then we would like to describe the different stages of the cutoff process based on this specific event in Spain, starting with the 24th of October and ending on the 2nd of November. After that, we will describe the impacts of the cutoff low and the weather based on this specific case. And last but not least, we will describe how the cutoff low gets integrated into the main upper level westerly flow. Okay, an upper level low, that's the first term. There are 3 relevant technical terms that we're going to use in this presentation and which we would clarify first. The first term is the upper level low. Upper level lows are, according to the EUMeTrain site, are closed cyclonically circulating eddies in the middle and upper troposphere. They are sometimes called cold drops because the air within the upper level low is colder than its surroundings. As opposed to this term, we've also got the cutoff low, which is an upper level low with a corresponding surface low. And then we found a term called DANA, that stands for Depresión Aislada en Niveles Altos, which is Spanish for isolated depression at high levels. And this term was frequently used by Spanish meteorologists and the media, so we thought we include that term as well. All right, so let me come to the first development stage, the upper level trough stage, which we can find in our example over the Atlantic Ocean on the 24th of October this year on 0 UTC. Every cutoff process starts off by the formation of an upper level trough. On the left image, you can see a GFS model weather chart from the 24th, in which the 500 hectopascal geopotential is indicated as black lines, and the color shading represents the temperature field in degrees Celsius in 500 hectopascal. On the right chart, you can see the 500 hectopascal isohypses, the contours in blue, and the isotherms are represented by the dashed green line. For the initial stage of a cutoff process, upper level trough then needs to amplify. On the right picture, you can see how the temperature wave needs to fall behind, so the trough can behind the trough, so that the cold air advection can cause the amplification of the trough. Also, the jet stream is of quite a significance. Quite often, the amplification process is supported by a jet streak, which is embedded on the backside upstream side of the trough. And this constellation is called a digging trough. The jet streak causes a net import of positive vorticity advection into the axis of the trough, on the base of the trough, which subsequently leads to its amplification. So the jet streak, so to speak, pushes the trough furthest to the south. And this can be seen on the right chart, which shows the wind speed in knots on 300 hectopascal. And there you can see on the 23rd, the trough above the Atlantic Ocean with already quite intense jet stream on the backside, and which becomes more apparent on Saturday and the 26th of October. Okay, now I would like to hand over to Melissa Wirtz, and she will be talking about the tear-off stage.
Yes. On the slide, you can see the second development stage, the tear-off stage. The map shows on the left the weather situation as of October 2024 at 18 UTC. As a result of the continued amplification process and intensifying upper level ridge, closing in form behind the star begins to look like inverted omega. Bit by bit, the star starts to separate it from the main airstream, and an isolated currently on cold air begins to develop. The third step is the cutoff process on 27th of October. The ridge overtakes the star and chooses the star to cut off from the main floor. It is now fully transformed to an isolated upper level low. The inflow of cold air into the core, the upper level low, is now fully blocked, and due to diabatic warming, the cold air pool in the core starts to warm up a bit. The next map shows an impact on the weather. The colored area represents the temperature distribution in 500 hectopascal. The black lines represent the isotopes, and the same high and the white lines represent the ground pressure distribution. On Monday, the 28th of October, on the left side, the upper level low moved further south and is now located to the west of the Strait of Gibraltar. Additionally, a surface area of low pressure begins to form on the night, which chooses the upper level low to transform into a cutoff low that you can see on the right. And now Saskia Mai will continue with the importance of the jet stream.
Yes, as Melissa already mentioned, I would like to tell you something about the importance of the jet stream and its lifting areas. On the right chart, you can see a jet streak and how the different forces, the Coriolis force in green and the pressure force in yellow, change by passing through an area of increased wind speed. The temporary imbalance of the forces in the entrance and the exit region induces areas where air masses are lifted and areas where air is forced to descend according to the continuity equation. In the right entrance region and the left exit region of the jet streak, the imbalance of forces leads to divergence in the higher troposphere, so to lifting areas, whereas in the other corresponding regions, the imbalance leads to convergence, so to descending areas. On the left chart, you can see the position of the jet stream on the 29th of October 2024 at 6 UTC. As you can see, the right entrance is above Africa and the left exit above the east coast of Spain with the lifting parts, whereas the left entrance region with the descending air is above the coast of Morocco. This is important to remember because now I would like to show you the lifting areas because of the PVA. Quite often, two axes can be observed where the isohyps are packed. The maximum of PVA is to be found at the front of the axis. In our case, the original trough axis had a positive tilt, which led to a higher pressure gradient in the southwest and northeast. The left jet exit above Spain leads to an increased lifting, and the left entrance above the coast of Morocco with the descending air leads to less lifting there, although it is in front of the axis. The axis is shown with the black line in the image. So on the next slide, I would like to show you additional factors. The sea surface temperatures were at around 20 degrees Celsius, which caused the air to become increasingly more moist while moving across the Mediterranean. As one can see in the right chart, where the precipitable water, I will say it as ppW, values are shown. So the blue color above Africa represents less ppW, and the reddish colors above the Mediterranean Sea show a high water content. Also, there are orographic lifting effects in Spain due to mountain ranges on the east coast, especially because of the Batik Mountain and the Iberian system a little bit north of it. The Batik Mountain is the one in the south. And the Central Mountains connected to the Iberian system in the west. Now I would like to show you some impacts on the convection. The warm sea surface temperatures and the cold air in the higher altitudes because of the cutoff low induced a high lapse rate. In combination with the high humidity, it increased the K values, which you can see on the right, the higher lapse rate on the left, always the regions above the Mediterranean Sea. Right, especially over the Mediterranean east coast. And now I would like to show you a sounding of the east coast of Spain on the 29th of October at 6 UTC. We use the DWD model Icon D2. As you can see, we have an increased cape and an unstable atmosphere. In the middle, an upper troposphere above 850 hectopascal. Near the surface, we have stable conditions. So in the case of lifting or heating, thunderstorms can be caused. On the next slide, you can see the radar and satellite image 3 hours later. Also, the thunderstorms or lightning with the little dots. As you can see, mostly on the windward side of the mountains, therefore mostly at the Batik Mountains, the Iberian System, and the Central Mountains. And these are also the regions you saw in our lifting image a few slides earlier. And now I would like to hand over to Ole, who will show you the cutoff over the time.
Yes, here on this slide you can see the development of the cutoff low and the jet until the 29th of October at 18 UTC. You can see in the upper left chart the cutoff low and the temperature in 500 hectopascals. At the ground there is the pressure in surface as well. And in the middle, there's lifting and the geopotential in 500 hectopascal, and in the lower right chart, there's wind speed and the geopotential in 300 hectopascals. And you can see that this configuration is similar as in the morning. And yeah, that shows the typical slow displacement of the cutoff that yeah, is typical for these weather phenomena. And you can see that the left exit region of the jet streak is still on the coast, over the coast of Spain, and there is a huge lift area over Spain in the middle, visible in 500 hectopascal. There is also a sounding on the next slide of the 29th of October at 18 UTC, which is from our icon model. And you can see that the instability is slightly decreased over the day, but is still there. So the thunderstorms are still possible to rise up. And yeah, that's something you can see on the radar and satellite image from the 29th of October as well, from 19 UTC. You can see the cloud bands above the central plains of Spain and above the windward side of the Iberian Mountains in the west of Spain. Yeah, there are large regions of rain, and there's a very high value of lightnings, which you can see in the right dots. Yeah, over the day, you can see in the 12-hour precipitation clusters until 18 UTC that on the windward side of the mountains, that they are caused stationary thunderstorms, and that they got often reactivated because of the orographic lifting. So there are rain values of 150 millimeters and more in local areas, and that was the 29th of October. At the 30th of October at 6 UTC, you can see the update of the cutoff low. It moved a bit northward, and the jet streak decreased due decreased temperature gradients that you can see in the upper left and the lower right chart on this slide. And we also have a sounding of our icon model from the 13th at 6 UTC as well. You can see the development. The cape got reduced after convective events. The atmosphere gets less unstable because of warmer air in the high levels and colder air in the lower levels of the atmosphere. And this is something you can also see in the satellite radar and lightning image, which I show you here from the 30th of October at 8 UTC. You can see that there are less thunderstorms than the day before, and that these thunderstorms that still exist are in the Pyrenees. So there's still orographic lifting, but less than the day before. And you can also see a large rain area in the south of the Iberian Peninsula that only has a few embedded thunderstorms. And in the middle of Spain, there are some places where are no clouds anymore. Yeah, overnight there is also the precipitation cluster that we have here. Over 12 hours until 6 UTC, you can see that there is a small displacement of the long-term precipitation clusters, but there's still high persistency visible in the center of Spain, in the Iberian system, and in the central system of the mountains of Spain. And now comes our fourth and final stage of the development stage of a cutoff low. The cutoff low warms up and weakens due to convection and surface level friction, and it continuously integrates into the main westerly airstream again. And now I hand to Ryan, who continues.
So that was our presentation on the cutoff low that caused the high precipitation rates in Spain this October. Thank you very much for listening and tuning in.